Hello everyone. So last class we will see the frequency response for some factors. So in this class we are going to complete the remaining factors also. So just once again, Bode plot is a frequency response plot. We can draw the two different graphs separately, magnitude plot and the phase plot, right? Okay. So last class we will complete these terms. Constant gain, integral factor and the derivative factor, right? Hope you remember what is the magnitude slope for the integral factor. Magnitude slope for the integral factor is always minus 20 decibels per decade, and the magnitude response for the derivative factor is always plus 20 decibels per decade. It is minus 20, it is plus 20, right? So please keep that in mind. Next, we will see that first order in the denominator. First order in the denominator factor. So let us take in one transfer function g of s equivalent to 1 by 1 plus st. Is it necessary to take that 1 by 1 plus st means? It is not necessary. You can take any function 1 by 5 plus st, k plus st, whatever it may be, but it must be satisfied that first order in the denominator. What is the order? How to calculate order? So order will be calculated in different criteria. So first one is the number of roots. The total number of roots of the given function will give that order of the system. Or else the highest order in the s coefficient of the denominator polynomial here is also gives that order. Here I am having the s power 1 so that it is corresponding to the first order. Or else, if you are equating that to 0, we will get the only one root, so that is it is belongs to the first order. So first, what is the basic step? We need to convert into that S domain normal transfer function to frequency function. How to get? Just by converting, letting s equivalent to j omega, so that we can write g of j omega equivalent to 1 by 1 plus j omega t. So what is the magnitude of this term? So 1 by square root of 1 plus omega square t square. And what is the phase angle for this denominator term? So directly I am writing in the numerator. So minus of tan inverse of imaginary part omega t. So that is minus tan inverse of omega t by real part is 1. So that we will get that only minus tan inverse of omega t. Tan inverse of omega t. So here instead of taking here directly omega value, so from the first order factor onwards, we need to separate that two regions. So that is the lower frequency region and the higher frequency region. So the frequency at which it will divides the magnitude at the low frequency and that high frequency is known as corner frequency. Okay, what is the meaning of corner frequency? Corner frequency will separate the low frequency region and the high frequency region. The frequency at which it will having that low frequency and high frequency separation, that frequency will be known as a corner frequency. Let's see here, for example, if I am taking it at the low frequency, this omega t value is very very small compared to this one. Omega t value is far less than 1. What it means that omega t value is far less than means what is the magnitude? So omega t value is approximately negligible. What is the remaining part? Only 1. So square root of 1 becomes 20 log 1. So what is the value of 20 log 1? 0 decibels. That means at the low frequency regions, the magnitude response for the first order factor is always 0 decibels. Always 0 decibels. Next, if you are taking that at the high frequency regions, that is this omega t value is far greater than 1. So that we will neglect this value 1. Directly I am taking that only omega t. Only omega t. Only omega t. So that what will get? Minus 20 log of square root of omega square t square. So that is omega t whole square. That square and this root get cancelled. The remaining term what will get? Minus 20 log of omega t. 20 log of omega t. Now we are substituting different frequencies. So first, initially at omega equivalent to 1 by t. So omega value 1 by t means tt get cancelled. What is the remaining term you will get? Minus 20 log 1. What is the value of 20 log 1? It is 0, 0 decibels. Now if you are taking that omega value is 10 by t, so tt get cancelled. What is the remaining term? 10. So how much you are getting? 20 log 10 means it is a 20. So you will get that minus 20 decibels. Can anyone observe here? What is the frequency deviation? Again, we are taking in terms of decade frequency 1 by t and 10 by t. And what is the magnitude change? Again, it is a 20 decibels. So 0 to minus 20 decibels. And now let's see the phase angle. So what is the phase angle formula here? Tan inverse of minus omega t. If you are initially substituting omega value 0 into this equation, tan inverse of 0, how much it is? 0 degrees. As what is the maximum frequency? Infinity. When the frequency is infinity minus tan inverse of infinity, so what is the value of tan inverse of infinity? 90 degrees, so that you will get the minus 90 degrees. So as the frequency is varying from 0 to infinity, the phase angles are going from 0 to minus 90 degrees. So that is the meaning of this. So if you draw the magnitude plot for the first order factor in the denominator, so WC equivalent to 1 by T and 10 by T. Why we are writing WC here 1 by T? So this is the transfer function standard function 1 by 1 plus ST. Then the frequency can be obtained from this term is here. So omega equivalent to omega c equivalent to 1 by T. So this 1 by T will be indicates the corner frequency. For example, if I am having 1 by 1 plus 4s, 4s, then what the corner frequency means? 1 by 4. That 1 by 4 frequency will separate the low frequency region and high frequency region. So until this 1 by t value, the magnitude is always 0 decibels. Yes or not? So until this one. Next, once the corner frequency is 1 by t, then what's the magnitude here? 1 by t to 10 by t minus 20 decibels per decade. What is the magnitude of the integral factor? Integral factor is again same, minus 20 decibels per decay only. But what is the difference? There is no 0 decibels. So please remember that point. So integral factor, the magnitude response is always minus 20 decibels per decay. But whereas the first order factor in the denominator is initially the magnitude is 0 decibels and then followed by the minus 20 decibels per decay. And what about the phase angle? So phase angle will be varying from 0 to minus 90 degrees as the frequency will be varying from 0 to infinite. Clear? So that's the difference between the integral factor and the first order in the denominator. So for the integral factor, the magnitude response is always minus 20 decibels per decay from the initial frequency to the final frequency. Whereas for the first order factor, initially the magnitude is 0 decibels until the corner frequency. From the corner frequency onwards, the magnitude is minus 20 decibels per decay. Can anyone tell now? What is the magnitude value for this term? 1 by 1 plus st whole square. Yes, it is initially it is a 0 decibels and then followed by minus 20 into 2 minus 40 decibels per decade, right? So just it is previously how we are multiplying n times, here also we can multiply with n number of times. Okay. Okay. And next, see, plus 20 decibels per decade, first order in the numerator. And then next, first order in the numerator. So if I am taking the function is 1 plus st, 1 plus st. So we need to convert this S domain into frequency domain j omega. Then I can write 1 plus j omega t. And if you're writing this in terms of magnitude and phase, So what is the magnitude for this term? Square root of 1 plus omega square t square and the phase angle is tan inverse of omega t. And if you are separating this magnitude 20 log of 1 plus omega square t square and the phase angle is tan inverse of omega t. Now can anyone tell what is the corner frequency? Again 1 by t, right? Because what is the standard equation? And please remember the standard equation should be in the form of 1 plus s a only. It is not in the s plus 4a. S plus 4 not like that. It is not in the s plus something, s plus t. It is not the standard form. Standard form is always 1 plus st. Then the frequency will be obtained simply just by multiplying this 1 by t only, 1 by st. So here we will get that 1 by t. Again, at the low frequency, we will neglect this omega t value is far less than 1 so that omega t get cancelled. Only the term is 1, so it is 0 decibels. And for high frequencies, omega t value is far greater than 1 so that we will get that omega t only. So that is 20 log of omega t. So 20 log omega t for 20 log omega t at high frequency regions. Now, if you are substituting t value, omega value is 1 by t, so 1 tt get cancelled, 20 log of 1, you will get how much it is? 0 decibels. Next, when omega value is 10 by t, so tt get cancelled. At frequency 10 by t, what is the value? It is 20 decibels. Plus 20 or minus 20? Yes, plus 20. So again, what is the frequency deviation? Decade. And what is the slope change? 20 decibels. Same as derivative factor only. But what is the difference? For the derivative factor, the magnitude slope is plus 20 decibels per decay. Just a minute. Okay. For that, for the derivative factor, the magnitude slope is plus 20 decibels per decay from initial frequency to the final frequency. Yes or not? What about this first order in the numerator? Initially, the magnitude is 0 decibels, and from the corner frequency onwards, the magnitude is plus 20 decibels per decay. Okay, that's the difference. And what about the phase angle? For the integral factor, it is 0 to minus 90, and for the derivative factor, it is 0 to plus 90 degrees. And you may get questioned that what is the phase value at the corner frequency of a derivative factor is always 45 degrees. What about similarly? What about that phase angle for the first order in the denominator at the corner frequency? How much it is? Right, minus 45 degrees. Okay. So first order in the denominator or first order in the numerator, whatever it may be, initially the magnitude is 0 decibels, and then from the corner frequency onwards, the magnitude is either plus 20 or minus 20, depending on the function. Okay. And then finally, the last one, quadratic factor in the denominator or second order in the denominator or in the numerator. Second order factor. So here let us see on the standard equation for the second order system is omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay, where omega n is the natural undamped frequency and the zeta is the damping factor. Damping factor. Again, it is not in the standard equation s square plus 2 zeta omega n s plus omega n square. So if you want to convert into the standard equation, so we will get. So what is the basic step first? S has to be converted to j omega, and then so we'll get the required form in this. So finally, we will need to convert into this notation. Okay, but mostly, we will get that first order factors only in the given transfer function. So very rare case you will get the second order function. So only one point you keep in your mind. For the second order transfer function, either in the denominator or either in the numerator, the corner frequency Okay, the corner frequency is always omega n only. Okay, the corner frequency is omega n. For example, if I am having that 100 here, 100 by some s square plus something plus 16s plus 100, then the corner frequency for the given transfer function is 100 square root of 100. 100 means 10 square. So that is value of 10. So 10 is the corner frequency which will separate the low frequency region and high frequency region. Can anyone guess what is the magnitude for this magnitude response for this denominator factor? What is the order here? Right, second order, s square. That means here we will get that magnitude is minus 40 decibels, right? 0 decibels followed by minus 40 decibels. And the phase angle is 0 degrees to minus 180 degrees. Okay. If you am taking the different damping factor values, zeta value zero point 0.1 or zero point 0.3 or zero point 0.5, 0.7, its magnitude response curve will be little bit changed. Its peak value will be changed. Okay. So for the second order factors only, please remember the corner frequency is always equivalent to omega n. If it is a second order in the denominator, the magnitude is 0 to minus 40 decibels. If it is a numerator factor, the magnitude is always 0 to plus 40 decibels. And the phase angle is 0 to minus 180 for the denominator, and for the numerator 0 to plus 180 degrees. At the corner frequency, phase angle is always 90 degrees only. Okay, hope it's clear. So just once again, we'll go to the brief recollect of all the points. So basic factor of any transfer function is either constant gain, integral factor, derivative factor, first order in the denominator, first order in the numerator, and quadratic factors. And quadratic factors. So always we need to give the first priority for the integral factor or derivative factor. I can neglect this constant. Why? Because this directly, suppose I'm having 5 by s, don't take 5 as a constant, one factor, and 1 by s as a one factor. 5 by s itself as the integral factor. Or else 10s. 10s itself act as a derivative factor. And please don't be considered 10 is a one constant and s is a derivative factor. 10s itself as a derivative factor. So that's why firstly, we will give the priority for either the integral factor or the derivative factor, since the magnitude will be occupied from the frequency from 0 to infinity. Whereas first order or second order factor, initially the magnitude is 0 decibels, and after corner frequency onwards, the magnitude will be coming into the picture. That's the reason we always give the priority for the integral factor and derivative factor for the first one. Okay, then we will see the basic steps for plotting the magnitude plot. Okay, then we'll see this one.